creo que de alguna manera, pues como para, también para que conozca quién es la audiencia, pues le pediría a todos ahorita, después de que presente el doctor Leonelo Bautista, que pongan aquí en los mensajes, pues quiénes son, de dónde se conectan o de qué programa de estudios o de qué centro de investigación son, pues para saber con quiénes estamos conectados. Y después de presentarnos todos, pues sí pasamos a la actividad en inglés como tal. Entonces, pues le doy la bienvenida a esta actividad al doctor Leonelo Bautista. Él es médico, doctor en salud pública y profesor asociado en epidemiología del Departamento de Ciencias de la Salud Poblacional de la Escuela de Medicina y Salud Pública de la Universidad de Wisconsin en Madison, Estados Unidos. El doctor Bautista se graduó de médico en la Universidad Autónoma de Santo Domingo en 1983 y de doctor en salud pública con concentración en epidemiología de las enfermedades infecciosas de la Escuela de Salud Pública de la Universidad Johns Hopkins en Estados Unidos, en Baltimore, en 1993. Su interés principal como investigador son las enfermedades cardiovasculares. El doctor Bautista ha sido investigador principal en 23 proyectos de investigación con financiación externa, ha publicado 3 libros y más de 100 artículos en revistas científicas indexadas. El doctor Bautista es el editor asociado de otras revistas científicas y es profesor ad honorem de la Universidad Autónoma de Santo Domingo, en República Dominicana. Entonces es un honor tener aquí al profesor Bautista, que nos ha aceptado nuestra invitación a esta actividad de la Escuela de Salud Pública de la Facultad de Salud de la Universidad del Valle en Cali, Colombia. Este es un espacio internacional, pues que queremos que ante todo nuestra comunidad académica esté en contacto con idiomas extranjeros, pues por ahora al inicio, pues básicamente inglés y a veces portugués. Y pues al final de la charla, pues tendremos un corto resumen en español como para aclarar ideas, pero pues la idea es que la mayoría de la actividad sea en inglés. Bienvenido, doctor Bautista.
Muchas gracias, Andrés. Eh, para mí es un placer estar por primera vez haciendo una conferencia en la Universidad del Valle, a pesar de que estuve mucho tiempo en Colombia. Bueno, voy a cambiar a inglés en un
Sí.
momento, pero
Entonces, esperemos un momentico, ya se están comenzando a presentar los asistentes. Tenemos a Carlos Patiño, docente de posgrado de Administración de Salud. ¿Quién más se quiere presentar por allí, por favor? Bueno, creo que las otras personas por ahora no tienen
ok.
cómo escribir, pero lo pueden ir haciendo a lo largo de la exposición y al final hacemos un resumen de quienes nos acompañaban. Entonces, pasamos a la actividad en inglés, por favor, para compartir las diapositivas y empezamos la discusión. Muchas gracias, doctor Bautista.
Okay. Thank you, Andres. It's a pleasure to be with you this afternoon, presenting this work that we conducted a few years ago. I'm going to be talking for 20-30 minutes, and then we're going to have plenty of time for questions. The topic we're going to be discussing is the role of chronic stress, and in particular, hair cortisol in the development of hypertension. But before starting with the specific topic, I want to emphasize the importance of hypertension as a cardiovascular risk factor. About 30% of the world population is hypertensive. There are about 1 billion people in the world, so more than 1 billion people is hypertensive. Hypertension is the leading single contributor to the global burden of disease. You probably have heard about the GBD project. This is data from the GBD project. 19% of all deaths in the world are attributed to hypertension, and that's approximately 11 million deaths every year. The disability adjusted life years attributed to hypertension are higher than those attributed to risk factors like smoking, alcohol intake, obesity, hyperglycemia, and hypercholesterolemia. On the other side of the equation, the role stress is an important exposure for hypertension and other outcomes, because chronic stress, which I I use the acronym CPS because it's actually chronic psychosocial stress, but from now on, I'm just going to say stress, has been proposed as a potential risk factor for hypertension. And chronic stress is highly prevalent in all populations. And some studies suggest that stress increases the risk of hypertension, but other studies don't. And the feeling in my group is that the inconsistency on the results of some studies is in part due to limitations in the measurements of stress. And actually, measurement of stress is one of the topics that our group is now focusing on. So why are
sorry, a question. Are you going to share the slides also, or is part of the introduction? Please remember for sharing the slides.
I'm presenting the slides. Am I not?
No.
I was sharing before.
Laura, ¿tú las puedes
There it
ver?
is.
Yo no. Okay, thanks. Yeah. Now
can you see them now?
Yeah, I can see now. Thanks.
Okay. So I was saying that stress is also an important risk factor, even a health outcome. And in spite of that, we have problems to measure stress. There are two ways to measure stress, basically: self-reported stress and biological markers. And self-reported stress is unreliable because when you interview a person and ask them about stress components, those can change because changes in the environmental stressors, like, giving this talk will make me more stressful now than an hour from now. There might be also differences because each person have a different perception of his or her inability to cope with the stress. And there are differences also in behavioral and biological responses to stress. You have seen that some people, they just seem not to get stressed at all independently of the circumstances, while other people, you might say, they're overreacting to stress. And regarding biological markers, there are also problems in measuring stress because the biological markers that we've been using based on the physiology of stress are measurements of cortisol in blood, urine, and saliva. And those are also highly influenced by circadian rhythms and transient stressors. Like, you probably all know that cortisol decreases during the night and then increases in the morning. So that the classification of a level of stress on an individual based on measurements in the morning would be different from measurements in the classification based on measurements in the afternoon. I think so. Based on that background, we decided a few years ago to measure the association between hair cortisol and hypertension. And the reason why I'm going back a bit. The reason why we decided to use hair cortisol is because hair cortisol provides a cumulative retrospective measurement of cortisol level over 3 months. So if you take the hair of a person and measure the level of cortisol, that would give you an average exposure during the last 3 months. And that measurement is not influenced by circadian rhythms or transient events. So in our study, we did a cross-sectional study and a nested sample in the SHOW study. The SHOW study is the study of the health of Wisconsin, which is a survey in a representative sample of the population of Wisconsin. And we did it in a simplistic way. We just decided to recruit participants that were enrolled in SHOW as far as they were eligible, and the eligibility criteria were to be 30 to 60 years old, which is consistent with the show eligibility criteria, and to have enough hair to take a sample. And that's hair from the back of the scalp. And we excluded pregnant women, people who work night shift, and people who were using injected corticosteroids, because all those would distort the level or the average levels of cortisol. So for our exposure measurement, as I said, we use hair cortisol as our main exposure measurement. And what we did was to take a sample of about 7 micrograms of hair, just cutting with a scissor. And then we process that sample and apply an ELISA test that had a sensitivity of 1 nanogram per milliliter. And this is the same ELISA test that we use in clinical work to in the clinical setting to diagnose Cushing syndrome. So you're surely have available in Cali. And then we define exposed individuals as those who have a level of hair cortisol greater or equal than 78.1 picograms per milligram of hair, which was the median value in our study sample. We also measure self-reported stress as part of the parent study of show. They were using the depression and anxiety stress scales, the DAS-21, the short version. And we classify as exposed, which is, I mean by that, as individuals with high stress, those who have a DAS-21 higher than 15. And our outcome was blood pressure. We measure blood pressure using an automatic oscillometric device that have been previously validated. And this was a model from Omron. And we took 3 measurements using a standard protocol for blood pressure measurement. And once we had the data, we discarded the first measurement and used the average of the last 2 in our analysis. The reason why we discard the first measurement is because that measurement, independent of what device you use and what setting you use, is usually higher than the following measurements. So if you use the first one and take the average, you're going to overestimate blood pressure. We defined hypertension as individuals with a systolic blood pressure greater than 140 or diastolic blood pressure greater than 90 millimeters of mercury, which is a standard, even though now we use a different definition of hypertension. For research purposes, this continues to be the best approach possible. And we also classify as hypertensive individuals who were taking blood pressure medication that was prescribed by a physician. So how we did the analysis? We use logistic regression. You probably all know about logistic regression. I'm going to add some details later on, but the key issue when we use any regression model is what variables should be in the model. And what was different in this study is that you used directed acyclic graph to select the variables that we would include in our model. Directed acyclic graph is an approach for variable selection that allows you to select a minimum set of variables such that if you include those variables in your regression model, you will get an estimate of the effect of the exposure that is unconfounded. Or in other words, you will get an estimate of the effect of the exposure that corresponds to a situation where the exposed group are comparable to the non-exposed group. Once we draw our DAC, we use a mathematical criteria, which is called the backdoor criteria, which was created by Peter. And using that criteria, you can identify the minimum set of adjusting variables. And I emphasize that that minimum set are the variables that will be in our model. So we don't play around with our models, entering and taking variables in and taking variables out. Once we define, based on the DAG, what variables should be in the model, those variables remain in the model. We only make decisions about the form that those variables would take in the model. So what were those variables? The minimum set of adjusting variables included age, gender, race, obesity, and alcohol use. Unfortunately, we only have one person that was not a Caucasian, and that's not unusual in Wisconsin, because only 8% of the population in Wisconsin is African American. And in all models, we included an age by gender interaction, because it is well known that after 50 or 60 years old, arterial stiffness increases more in men than women, and that makes the blood pressure in women higher than the blood pressure in men. So in all models for hypertension or for blood pressure, I always include an interaction by gender and age. Now, this study has a big limitation, which was that we had a small sample size. And the solution that we implemented, because we have a small sample size, was to use approximate Bayesian logistic regression. And I might provide more details on that, but later on, if there is interest. But a Bayesian logistic regression, basically what we do is to formally incorporate the knowledge that we have about the relationship between different risk factors and hypertension in our model. The statistical approach we use to fit this model is a simple statistical approach. I say simple because it's simpler than Bayesian approaches that are based on Markov chains and sampling from the posterior distribution. So we use what is called penalized likelihood data augmentation, which if you have a course on epi methods, you probably know what it is. When we have a 2x2 table with zeros in a cell, it is impossible to estimate the risk ratio or the odds ratio. And one recommendation is that you add one observation to each cell. And penalized likelihood works the same way. What we do is that we add observations to our data based on what we know about the relationship between hypertension and particular risk factors. And that is expressed, or how many individuals we add to our analysis is based on the prior estimates of the odds ratio. For example, we use a prior odds ratio that have a log normal distribution with bounds from 1 to 4 for the effect of the level of hair cortisol. And later on, I'm going to explain why 1 to 4. But right now, what I'm saying is, when I do my analysis, I'm assuming that high levels of cortisol do not prevent hypertension. And that's why the lower bound is 1. And I'm saying high level of cortisol do not increase the risk of hypertension more than 4 times. And then we use also prior odds ratio for the variables that we included in our logistic regression model. For example, if we included the variable alcohol intake, then we will look for a prior odds ratio for alcohol intake to include in our model. But to do that, we use data from NHANES. NHANES is the National Health Survey, Health and Nutritional Survey in the US. And we took the data from 1999 to 2004 to obtain those prior OX ratios. And those OX ratios were meet the requirements in this case because they were independent of data we were using for the analysis. And then once we run the analysis, we took samples by bootstrapping 1,000 samples to get 95% credible intervals. And after we completed our analysis, we did what we call a bias analysis. You probably have heard about bias analysis with the name sensitivity analysis, but currently the term bias analysis is preferred because what we want to do in that analysis is to figure out how much uncertainty bias introduces in our estimates of the effect of the exposure on the outcome. For example, in our bias analysis, we change the prior for the effect of hair cortisol. Remember that we say it's going to be 1 to 4, but in our bias analysis, we use a prior that went from 0.73 to 3.10, which came from previous studies of the association between stress and hypertension. We excluded hypertension-aware individuals in our analysis to address any potential bias due to reverse causality. And basically what we mean by that is that people could argue that whatever we observed in the study was a consequence of people who know they were hypertensive being more stressed out than people who knew they were not hypertensive. Then we use the E-value to assess residual confounding. The E-value is a assumption-free method to assess confounding that was developed by Dean and Vanderwill. And when I present the results, I'm going to explain exactly how the value works. But right now, I'm going to tell you that this is pretty easy to use because it's a very simple formula. And then to interpret the results from our E-value analysis, we compare our results with the odds ratio for determinants of high cortisol, hair cortisol levels in other studies. And I'm going to show you exactly what we did. So these were the results of our studies. This is a traditional table 1 in any study where you compare exposed people to non-exposed people. Okay, and you can see that in this comparison, we have people with high hair cortisol, low hair cortisol, defined as we previously mentioned. And you can see that older people, people with high hair cortisol have a tendency to be older. They have a higher tendency to be obese. They have a higher tendency to be older than 50, which implies that these variables could be important confounders to include in our model. And you can see also that the mean blood pressure in people with high levels of hair cortisol was higher than in people with low levels of hair cortisol. And the same thing for diastolic blood pressure and for hypertension. See, I'm going to mention that I never make a test comparing these two groups because the test doesn't tell me anything that I need to know. All I need to know is whether the distribution of the variables differ based on the difference in the distribution of the variables, I can make a judgment of whether I can adjust for that difference or whether I'm doomed I will not be able to adjust, for example, by gender. Let's say if only 2% of our population were men, then I would say, we're not going to be able to adjust for gender. So we might be better off doing the study only. So these are the results of our analysis, the odds ratio, hypertension by her cortisol levels, and the type of analysis. Even though we did a Bayesian analysis, we started with a frequentist analysis, a traditional analysis, including the same variables in our model. We fit a crude model, an adjusted model, and another adjusted model in which we included a stress, but this is the stress, the self-reported stress. So a frequentist analysis is similar to a Bayesian analysis. The main difference resides on the limits for the prior odds ratio. The prior odds ratio in this case goes from 1 divided by infinitive to infinitive, which means any effect of the level of cortisol on hypertension is equally valid. So it could be the level of her cortisol could be highly protective or highly harmful, which doesn't correspond with the reality. So you can see the odds ratios for that analysis. The adjusted one is 3.6, which means that the risk of hypertension increases almost 4 times in people with high levels of cortisol. But the 95% credible interval is not, includes 1, so that we're not confident that her cortisol increases the level of the risk of hypertension. So we did a Bayesian analysis with the same 3 models, and you can see these are the priors that we're using for those models, 1 to 4, as we defined before. And you can see that the effect of the fully adjusted model is an increase of 100% in the risk, or the risk in exposed people was 2.2 times higher than in non-exposed people. And you can see that the credible 95% credible interval suggests that there is a high chance that high levels of hair cortisol increase the risk of hypertension by 68% up to 200%. And we did the same analysis. You can see here, this is part of the sensitivity analysis or the bias analysis, modifying the prior odds ratio. In this case, the prior odds ratio was 7.72 to 3.10. And you can see that qualitatively speaking, the findings don't change much. So we went from 2.23 to 1.28. So that our choice of priors was not the main determinant of our findings. So the other thing that we did was to use, as we explained before, the E-value method to assess the impact of unmeasured confounding. And the way we assess this is by applying a formula that is a very simple formula. I'm not going to show it here, but once you have the results, you get a graph like this one. And in this graph, what we're seeing is the association between the confounder and the outcome. So these are odds ratios, 1, 2, 3, 4, 5. And the association between the confounder and the exposure. And in this case, any value that is above this curve would be a value that, if a variable exists that have that effect on the exposure and the outcome, it would nullify the effect of the exposure. For example, if we have an odds ratio, if a confounder that increases the risk of hypertension by 4 and the risk of exposure or the risk of stress by 3, then that variable could nullify our results. So what we found was that for a confounder that we didn't measure or didn't include in our model, to nullify our results, to make them statistically non-significant, that variable have to increase the confounder exposure odds ratio or risk ratio by 2. And in that case, if it only increases by 2, it has to be a confounder that increases the risk of hypertension by at least 5. So now that we know that, we can make a judgment call. For example, I know that no risk factor for hypertension is likely to increase the risk of hypertension by more than 5. And why is that? Because the strongest risk for hypertension is pre-hypertension. So if a person has pre-hypertension, within the next 5 years, his risk of developing hypertension would be 4 times higher than a person who didn't have pre-hypertension. So it is unlikely that any risk factor, any confounding factor that we didn't measure would increase the risk beyond the risk of hypertension by more than 5 times. And on the other side, I'm going to show you the effects of cortisol, different measurements of cortisol on the level of hair cortisol. So these associations that you see here are the ones that correspond to this axis of the graph. To this graphic, and this axis, the confounder exposure risk ratio. So you can see that none of those confounders get to 2. Some of them get very close to 2. But that's the point. That's why we put the point, this line in 2, because it shows us that it is not likely that a confounding factor will increase the prevalence of exposure by more than 2, but it's also unlikely that it will increase the risk of hypertension more than 2. So the bottom line of that is that the effect that we estimated in this study is unlikely explained by confounding. So the other thing that I did, or that we did in our sensitivity analysis or our bias analysis, which is the proper name, was to do an analysis excluding individuals who were hypertensive. And you can see the results here. When you exclude the individuals who were hypertensive, the odds ratio decreased to 1.95, and the 95% credibility interval went from 1.5 to 2.3. So that is also an unlikely explanation of our finding. Confounding is an unlikely explanation of our findings. So how do we interpret this finding? Well, basically that individuals with high levels of hair cortisol were twice more likely to be hypertensive, and that there was a 95% chance that they were from 68% to 204% more likely to have hypertension. Actually, there isn't any mistake in this. It's 104% more likely to develop hypertension. The other thing that you can appreciate is that we increased the precision of our estimate by formally incorporating existing knowledge in the analysis. The frequentist analysis, as we explained before, assumes that any effect of hair cortisol on hypertension is possible, which we know from that is not a likely assumption. The errors in hair cortisol measurement, if there was any error on the lab in our test to measure cortisol, they should have been non-differential, because those errors don't depend on whether the person was hypertensive or non-hypertensive. And in average, those errors will result in a odds ratio that is closer to 1, closer to the null, than if there was no error. So if there is any bias in this sense, it's a bias towards the null. And in spite of that potential bias, we detected a significant effect of the exposure. The other source of bias is selection bias. Selection bias could happen in this study because we were studying a sample of people who were alive. They were survivors, so we could have survival bias. But survival bias, which is a form of selection bias, in this case, would be unlikely to explain our findings because both hypertension and high cortisol increase the risk of dying. So if you take a sample of individuals who are survivors and measure the level of cortisol, and they have a high level of cortisol, then they probably don't have hypertension. And the other way around. So if there was selection bias, the bias would move the true risk, the true odds ratio towards null, towards 1, instead of away from 1. In other words, the bias that we could have in this study cannot explain the observed association between hair cortisol and hypertension. So I think this is my last slide. How do we interpret this finding? Well, we interpret this finding saying there's a good likelihood that hair cortisol is a good measurement for chronic stress, and that hair cortisol is a likely risk factor for the development of hypertension. And why that happens is because a sustained elevation of blood cortisol will result in a sustained elevation of hair cortisol, and it would downregulate the glucocorticoid receptor. It would result in cortisol resistance. It would result in diminished anti-inflammatory response, mild chronic inflammation, and mild chronic inflammation increases blood pressure and increases the risk of hypertension. Also, elevated levels of blood cortisol increase intra-abdominal accumulation of visceral fat that results in obesity, and obesity is a known risk factor for high blood pressure. Also, high levels of cortisol increase salt retention, which is a risk factor for hypertension, and increase insulin resistance, which is also a risk factor for hypertension. So in this study, what we try to show or what we show in terms of using a study that was a low-cost study with a small sample is how we can take advantage of what we already know and what we are studying to design, analyze, and interpret our study. And now I'm open for questions.
Okay, thank you very much to Professor Leonelo Bautista for this very interesting presentation. I have read the article and now I understand more things after your oral presentation. Thank you very much. And something that I want to emphasize, to highlight this is a very strict, rigorous methodological approach, and that's the methods that we are following now in epidemiology during the 21st century. And I am going to mention a lot of topics in relation to the methods that you have applied in this study. And please explain a little bit more to the public on these topics. And first of all, I would like to mention I have seen that this is a big health survey in Wisconsin. You have some kind of I have read the other paper, and it seems that you are collecting yearly data, adding to a longer survey methodology, but it seems that each year, that's my question, each year is around 800 to 1,000 people in the yearly survey. And what do you have to deal with a small sample size if the big survey in Wisconsin in Wisconsin has hundreds of people.
Well,
Why do you need to deal with a smaller number?
Well, because we have little money to pay for the test. That's the truth. But we didn't have money to pay for 1,000 measurements of her cortisol. And let me tell you, there is a limitation on this, which is that you cannot include bald people, and not everybody is willing to give you a hair sample. And I remember that one colleague once told me, she was involved in the study, and told me, you're going to end up with a sample of hippies in your study, which is not a big problem. It's not a limitation, really. But that's a limitation. It's not that it's not possible. It is possible, but some people will have to be excluded because they don't have enough hair to provide a sample, and you have to pay for the testing.
Oh, okay, that means that you need to rely on the people who was approaching to the field work for having this special biochemical measurements and biochemical process that was expensive. Yeah.
Yes. What was expensive was not recruiting the individuals, because that was part of show, but was paying for the testing, because the testing was conducted in the Wisconsin State Lab of Hygiene, and we had to.
Okay.
They were not part of this. Those tests were not part of the study of show.
Okay, and the measurement of hypertension was doing at the same time when you collect the hair
sample
data, the hair sample. Yeah.
Yes, that's correct.
Okay. Yeah, I can see that. Could you as another option? Could you have done a case control study, taking into account that you were able to measure the hypertension in that moment, and then to try to collect the sample from from the cases and from a number of controls? What would be a good approach, or what disadvantage did you think that you have with the case control approach in this case?
Well, I could have, but if I did it that way, if we did it that way, then we would not have had opportunity to measure blood pressure or to study blood pressure as a continuous variable, because most of these people will be treated. And it's not that problem is not addressable, but with a small sample size, it would have been difficult. And the other reason why we did it is because, well, we knew that at least a third of the population participants would be hypertensive. So we will have a large enough sample of cases, because hypertension is not a rare disease. Basically, at that age range, you will have like 25% of the population.
25, yeah. Okay.
Well, we have 27, actually, 27%, I think.
Perfect. And the other question is, then you explained that because your small sample size, you need to address the problem with Bayesian statistics. How was the sample size calculation? It's similar to to frequentist sample size calculation. Do you need something special around this special sample size calculation for Bayesian statistics?
I didn't calculate sample size, and usually this is a practical thing. More sample size calculations are manipulated, and we manipulate them. I would say, if I have a million pesos, or let's put it, if I have $30,000 to do a study, I'll figure out how to do the study that is most efficient with $30,000. And that implies that I'm not going to calculate a sample size. I'm really going to figure out what distribution of cases and controls would give me the most precise estimate. And once I know that, I will tell you that's the sample size that allows me to get a 90% power. But in fact, that sample size is driven by how much resources I have.
Okay,
That's what
perfect.
most people do. And you could calculate sample size using for a Bayesian analysis, but if you calculate it for the frequentist analysis, you will know that you will gain information with the Bayesian analysis. So the Bayesian analysis is a trade-off between validity and precision. With the Bayesian analysis, you gain precision, but you might lose validity if your priors are wrong. So you have to take a good care of selecting your priors when you select your priors. But that's a way to incorporate what you know about the subject. We should not assume that, well, we don't know anything about hypertension, and we can expect that having a stress is going to be protective. So that knowledge, you can incorporate it in your analysis. And you know that with the Bayesian analysis, you will get more precision.
Okay, thank you. And in relation with Bayesian analysis, please explain us a little bit more about the priors. How do you select a good prior according to the state of the art of the knowledge on a health problem? How was that conceptual and also methodological procedure?
Well, the issue of selecting priors is one of the main hurdles when we want to use Bayesian analysis. You have to keep in mind a couple of things. For example, your priors must be independent of your data. For example, when we selected priors for variables like gender, age, obesity, we didn't take those priors from the show study. We took them from the enhanced study, which is a different study. We could also have look at the literature for priors for those variables, but we had the enhanced data at hand. So we could generate those priors from an independent data set. The second thing that you have to keep in mind is that you can do a partially Bayesian analysis where the only prior you include is the one for the exposure of interest. And that should be relatively easy to do, because if you can concoct an odds ratio or a risk ratio to do your sample size calculation, that means you have a prior to. But the best way to do it is the way we did it. What we did was to look at the literature and see all the studies of stress. What were the effects on the risk of hypertension, and did a meta-analysis for that. And from that, we took our prior. And the same thing you should do for other variables that you are going to include in your model, because you already know what variables you're going to include in your model. And you can go to the literature or to another database to get those priors.
Oh, okay. That means that the other risk factors they have their own prior function. For example, for
yes,
let
they
me
did.
say to be a male, to have abdominal obesity, and so on. Each variable has its own prior.
Yes, that's a full Bayesian analysis.
Okay. That means that it's a complex task, because you need to looking for in the literature the proper function or at least the proper limits of priors, because you have decided priors between 2 points. As I have seen the extreme variables from the literature, as I understood.
The proper form for the priors when you're doing studies like this is not that difficult, because like when you calculate a confidence interval for an odds ratio, you assume that it has a log normal distribution. So you use a log normal distribution for your prior also. Okay. So you think what you should put in your model. And so it's not that difficult. Figuring out priors is is more difficult when you have to define a prior in a model that you have to specify the mean and the standard deviation, but you don't have data from where to get those. And particularly the standard deviations of the variance, they're very difficult to figure out because we don't think in that scale.
Okay. That's why most of your variables are dichotomic, because you only need to define, for example, an odds ratio function.
Right.
Okay.
I include them all as dichotomous also because my sample size was still small.
Okay. Very interesting. Thank you very much. And here we have a question from Carlos Patiño. Thank you for the study. I would like to see this kind of study with workers as well, because as we know, stress is an issue important for every job, every company. He's asking about the workers. Did you have workers in this sample size? In this sample, sorry.
Oh, sure, but we didn't focus on that, and we have workers because this is a random sample, so we select people at random, so they might have different occupations, but we're interested in working on high levels of stress. For example, we were very interested in doing a study in our med students, but it didn't fly. So sometimes we want to, and this is kind of premature, but we're thinking to do something similar, not similar, something in workers from the Universidad Industrial of Santander.
Okay, perfect.
Yeah. So if there is interest on that perspective, we can talk about it.
Okay, very interesting. And I have another question. This is a cross-sectional survey, and here we have a chronic disease, a chronic pathology. But what do you think about the latent period in relation with the chronic measurement of cortisol, of hair cortisol? How because this is cross-sectional, and when we have cross-sectional studies, we need to disentangle the order, the timing of each variable. How good is hair cortisol as a chronic exposure before hypertension? How do you deal with the order of the causal order of variables in this cross-sectional study?
Okay, well, that's a pretty good question, and it has two components, and I'm going to start by the first one, which is the temporal relationship between exposure and outcomes. The criterion for that relationship is sometimes misunderstood. There is no requirement for the exposure to precede the outcome. There is the requirement for the exposure not to follow the outcome. And if you think about Rothman models with the pies, the causal pies, he clearly distinguished between a risk factor and a cause. A cause is a combination of combination of risk factors that is sufficient to generate the outcome. So the last component in a cause, the time from that component to outcome is zero. So the actual requirement is it has to be before the outcome or at the time of the outcome. And you can think about examples like, well, if you're drunk and drive and have an accident, well, you could just, there is no time from being drunk and having the car accident, right? So that's the first thing that I wanted to clarify. But in our study, you could say, well, you don't know what happened, what was first. But remember, the measurement of cortisol that we have is from the 3 previous months, which doesn't mean that the person didn't have hypertension even before that. And that we recognize. But I would say that the fact that you become hypertensive might stress you or might not, right? So the stress could be a consequence of hypertension. And that's what we try to address when we did the analysis, excluding people who knew they were high. If I found that the effect when I exclude those people is completely different or is null, I would say, you know, what's going on here is that people become really stressed when they develop hypertension. But that's an issue that we have to address and that we hope we will.
Great. It's a great explanation about the order of variables of risk factors, because sometimes the people say that not cross-sectional, we have nothing to do with we have nothing to do in relation with risk factors or whatsoever if we are using a cross-sectional study. And in a lot of textbooks, cross-sectional studies are like the Cinderella of epidemiology, because that. But it was here is very interesting how you and your research group deal with the order of variables and questions in relation to risk factors. As I don't know if it's your same opinion, but I have seen that cross-sectional studies as some kind of Cinderella in epidemiology, but here we are dealing with a very interesting cross-sectional study.
It all depends on the specific exposure, because there are exposures that you could say, well, that happened before the outcome. Like if you measure a genetic marker, well, that happened before the outcome. If you measure something like cholesterol, and your outcome is, let's say, heart attack, well, I can assure you that the levels of cholesterol will increase before the heart attack.
And also after the heart attack?
They could be changes after the heart attack, but in most cases, those levels of cholesterol, they were high before the person, because the mechanism for the person to develop a heart attack is, they get atherosclerosis, they get high cholesterol atherosclerosis and atherothrombosis, and then the heart attack. So, and that's why our studies work. Like we measure blood pressure today, and then we follow you up, and we find that the outcome, but we don't know when you became hypertensive. And that happens with all continuous variables. And the extreme example is, well, if you measure the effect of gender, well, that precedes any outcome. Or the effect of a genetic marker, that precedes any outcome.
Okay.
And regarding the, let me make this comment. Regarding the issue of temporality, there are methods now that allows you to figure out in some circumstances what was fair first, the egg or the chicken.
Yeah, that's something that we mentioned here,
and that's something.
The egg and the chicken, great. And even in the cross-sectional approach, it's possible to deal with the order in a cross-sectional approach.
They're mathematical methods. They're not widespread. They're not easy to use. I don't know how to use them. I'm very interested, but I've always been interested, as you are, in incorporating both type of data, cross-sectional and longitudinal, because we have, like in the United States, we have tons of cross-sectional data from NHANES, and it's not that frequently that you see that something that you observe in cohort studies, you don't see it in case control, in cross-sectional studies, well-designed cross-sectional studies.
Okay, I understand. And inside the NIH, I don't remember. It's National Health. NIH. Is the approach also a panel study? I mean, did you repeat the observation on the same people over time, or do you have a new? New sample?
It is an addition. It is a cross-section. It's a different sample in every way.
Okay.
However, there are studies embedded in NHANES with separate funding where they follow people. And NHANES also have mortality data that is longitudinal. Like now you can get the mortality data for people who participated in the first waves of NHANES. So it's not all, it's cross-sectional basically, but it doesn't prevent you from seeing outcomes like mortality. And let me tell you something for you and for everybody who is listening. NHANES data is free. You can use it anywhere you are. And you don't have problems to use it with the IRB because it's publicly available data. I've done a lot of studies with NHANES. Now I'm not that enthusiastic with NHANES, but it's just because I don't have anything that I want to see in NHANES, or I haven't been looking at NHANES later. But I think that people in our countries should take advantage of NHANES to do particular studies. One study that I did using NHANES data was the relationship between bilirubin level and blood pressure. And I follow the same principles that I follow in this study. And later on, people have verified that, yeah, there's an association between high levels of bilirubin and lower levels of blood pressure. And they have verified this in cohort studies. And I can tell you, have you heard that people in China have published more papers than anywhere else?
Yeah.
Well, many of those studies are from using NHANES data.
Wow, amazing. They have enough people to do in the analysis. Yeah.
Yeah.
A great number of researchers. Yeah.
But I think that this could be a very good resource for training in EPI and training in other areas, because you have all the data well collected, validated, hundreds of thousands of observations, and you can use it.
Okay, and yeah, for research or also for academical purposes, for example, to repeat analysis from a paper just to
Yes,
learn
you can do
the procedure and so on. That's very
you can do whatever you want.
it's
Completely free.
Great, thank you very much.
To anyone who has a computer and access to the internet can download the NHANES database. There is also another survey that one I don't have much experience. That is a survey that is just by interview, the National Interview Health Survey, and I have a lot of data. Well, you might say it's valid or is interesting for people in the US, but there are many problems that, well, they're interested for everybody anywhere. Like if you're interested in fatty liver and risk of breast cancer, you can do this study using NHANES data.
Perfect. So, and my last question, because I would like to listen the public also. My question is about the table number 3. I didn't understand how do you pass from the correlation from previous study to odds ratio here? How was that relationship?
Okay, yeah.
It's a different statistic.
There is a formula to do that, Andres. I can share it with you. I don't remember it, but I have it somewhere, and it's pretty easy to use. But you can compare from correlations to odds ratio and correlations to risk ratios also.
Okay, because that means that it seems that it's a correlation that is not the continuous one. It's another kind of correlation. For example, a tetrachoric or something like that.
No, it's a regular correlation coefficient, a Pearson correlation coefficient. You can
Okay.
convert it to an Ox ratio.
Okay, it's interesting to see how is the procedure. Please send us the reference I can share with the group. Okay,
Maybe I mentioned, did I put a reference on?
I see the source of the correlation, but not the formula. Maybe
No, the formula is not there, but I don't know whether
the source. Yeah. Maybe I
maybe
jumped.
I put a reference on how to do it. I'm not sure.
Okay, I need
But
to.
I can point you to where and how to do it.
Okay,
It's not complicated.
maybe it's in the explanation of the reference, of course. Okay, I would like to listen some colleagues and some students from the public, please. You can ask any question to Professor Leonelo Bautista.
You can ask me in Spanish also.
Also in Spanish, okay. If you want, we can.
It's fine with me. If you don't
Spanish, if you want, let's pass to Spanish. I think that we finish until this moment to the English part, and let's go to pasemos español y bueno, ustedes pueden hacer preguntas adicionales al profesor en español. Ya, si quieren cerramos hasta aquí la parte en inglés, pues que era un ejercicio académico que queríamos hacer, continuemos en español. Si tienen preguntas adicionales, profesor Leonelo, las pueden escribir también en la ventana de comentarios.
Okay, I see.
La pregunta de Carlos ya la respondimos. No sé si hay otras, si hay preguntas adicionales.
Don't be shy.
No hay preguntas adicionales, pero entonces sí me gustaría pues resumir al final lo que encuentro interesante de este artículo del profesor Leonelo Bautista y sus colaboradores, y al final el profesor nos puede explicar algo adicional, pero entonces es muy interesante ver ellos cómo trabajaron el problema de una pequeña muestra haciendo una aproximación bayesiana. Discutimos un poco durante ya la charla en inglés qué significaba la probabilidad anterior, o sea, a priori, la probabilidad a priori, que hay que tener en cuenta de cómo se calcula, cuáles son las fuentes, es la literatura la que se tiene que buscar para sugerir estas probabilidades anteriores y ya después el procedimiento que ellos hacen analítico con las regresiones logísticas bayesianas, pues con eso obtienen las probabilidades posteriores que son las oportunidades o ventajas relativas que vemos aquí en este estudio. Otra cosa muy interesante a destacar es cómo estaban más interesados en el papel del cortisol, entonces de los niveles de crónicos de cortisol, entonces el profesor Bautista lo que hace es tomar el cortisol en cabello que se acumula en un periodo de 3 meses o más, entonces basan los análisis en la cronicidad de los niveles de cortisol en los niveles que encuentran en cabello. Entonces, muy interesante este abordaje y sobre todo, pues que también sirve para diferenciar ese orden de las variables que a veces no queda tan claro en los estudios transversales. Esta fue la aproximación que ellos hicieron para diferenciar la cronicidad de la exposición por un lado y específicamente, pues, el desenlace en salud, que en este caso era un nivel de hipertensión que fue medido transversalmente. Entonces, y con este interés en el cortisol, pues proponen un diagrama unidireccional acíclico. Esto es más o menos como la propuesta de la traducción apropiada de qué significan este concepto grande en inglés. Entonces, un diagrama unidireccional acíclico, pues porque tiene flechas unidireccionales que proponen una dirección causal entre las variables. Ellos hacen esta aproximación y pues así identifican un número de variables que tienen que controlar como confusores para la relación entre el cortisol en cabello y la hipertensión que están identificando. Entonces, se utiliza este nuevo abordaje que está enfocado en factores de riesgo específicos para hacer el ajuste de confusión con los otros factores presentes, como muy bien lo mostró el profesor Bautista. Otros aspectos, entonces, a resaltar que vemos acá es el análisis de sensibilidad. Entonces, este es el análisis de sensibilidad de confusores no medidos o de error de medición en los confusores. El análisis de sensibilidad pues tiene varios componentes. En este caso, pues ellos intentan mostrar qué hubiera pasado, o sea, qué pasaría con los resultados al no haber medido un confusor fuerte. Entonces, para eso tenemos la figura 2 mostrando qué pasa con los confusores fuertes, y pues algunos de estos confusores ya no son realistas. Entonces se muestra que la forma como se afectan los resultados pues tendrían que ser unos confusores que ya son poco realistas según la literatura para afectar de forma importante los resultados. Y esto lo resume en la figura 2 con el análisis de sensibilidad. Entonces es otro abordaje adicional que tiene este artículo pues para aportar a su rigurosidad. Y a ver qué otro aspecto, a ver si lo perdí. Ah, bueno, además también, también hizo análisis de sensibilidad separando de las personas que tenían conciencia de su nivel de hipertensión, a ver si los resultados se afectaban. Los resultados no se afectaron, entonces le da fortaleza argumental pues a las conclusiones del profesor Leonelo. No sé, profesor Leonelo, si quiere agregar algo más de este resumen en español.
Ah, no, solo recomendar a todos pues que traten de ser sistemáticos en sus estudios, que no se basen en argumentos sin evidencia. Y yo creo que eso es algo que nosotros hicimos en este estudio, que fue para cada tipo potencial de sesgo, explicar cuál era la probabilidad de que ocurriera o evaluar cómo cómo podrían cambiar los resultados si ese sesgo ocurre. En lugar de estar tan enfocados en en ver si sus resultados son consistentes con los de otros estudios.
Perfecto. Laura, ¿se le puede abrir el micrófono a Carlos Patiño que quiere preguntar también?
Aló, buenas tardes. ¿Me
Buenas,
escuchan?
Carlos.
Buenas tardes, Carlos.
Buenas tardes, doctor Bautista. Primero que todo, muchas gracias por esta interesante conferencia. Yo soy un médico que trabaja en el área laboral, en el área de salud
Ujú.
nacional. Y como usted muy bien lo dice en su artículo, digamos que la medición del estrés que nosotros hacemos es subjetivo porque se basa en unas encuestas. Y realmente hasta la fecha, digamos, no tenemos un índice biológico que efectivamente nos diga que el trabajador está pasando por un periodo de estrés. Desafortunadamente, lo que vemos en muchas empresas es que hay una búsqueda de una ganancia secundaria de incapacidades, de días perdidos, en fin, y todos atribuibles al estrés. Pienso yo que, bueno, más que una pregunta, creo que es un comentario, pienso yo que a futuro podríamos complementar estas encuestas que nosotros realizamos para determinar los niveles de estrés en los trabajadores con estos índices biológicos que me parece que serían de gran ayuda para efectos de tener ya un diagnóstico más objetivo en nuestras organizaciones. Solamente quería hacer ese comentario y muchas gracias.
Sí, me parece muy bien, Carlos. Y fundamentalmente el estrés, el estrés podría ser un, un desenlace clínico ah, para el cual se implementaran tratamientos. Pueden desarrollarse tratamientos para manejar el estrés, aparte de los tratamientos de tipo psicológico y conductual. Pero la dificultad de medir el estrés impide que se utilice como un desenlace clínico. Y eso es algo en lo que nosotros también estamos trabajando ahora. Ah, básicamente, nosotros estamos trabajando en cómo determinar la validez de cada una de estas pruebas, aunque no haya aunque no hay una prueba gold estándar para medir estrés. Es posible, usando las distintas pruebas que existen para medir estrés, determinar cuál es la sensibilidad y especificidad de cada una. Y en eso estamos trabajando ahora.
Listo, muchas gracias. No sé, ¿hay más preguntas del público? Bueno, entonces, si no es más, de nuevo, muchas gracias al profesor Leonelo Bautista por participar en este espacio de la Escuela de Salud Pública de la Universidad del Valle en Cali, Colombia. Bienvenido acá personalmente cuando nos quiera visitar en la escuela. Y muchas gracias por su participación.
Con mucho gusto, Andrés. Cuando quieran. Y con mucho gusto pueden contactar por correo electrónico también para cualquiera de estas cosas. Ha
Listo.
sido un placer. Ok, Andrés, hablamos.
Muchas gracias. Buena tarde.
Siempre, Andrés.
Bueno, muy amable.
Buenas.
Muchas gracias.